Good evening, all. Let's begin the session in like another 2-3 minutes. So please do wait. We'll wait for like some more students to join. Okay, and then we'll start. Let's begin today's session. Am I audible? Let me know if there is any issue with
Yes,
the
ma'am.
voice today.
Okay, ma'am.
So let's begin today's class. So this week we'll be discussing boundary value problems of ordinary differential equations. So previous week we had discussed the previous week we had discussed the ODE IVP problems, that is initial value problems. So this week we'll be discussing the boundary value problems. So now moving on to the theory. So here we have a second order ordinary differential equation. What is second order ordinary differential equation? So just a second, let me just annotate. In case you have any problem with the audio today, please do let me know.
Okay, ma'am.
So earlier we had like ODE IVP problem in which we had at the starting point. So considering a road here, we had known what is the value here. That is at x is equal to 0, we knew what the temperature was, and sometimes if it is a second order ODE, we was also given what this T dash value was. But both this information was at x is equal to 0, that is the starting at the starting of the road. Now this time we have like ODE, BVP, ODE boundary value problems. So here, if you look here, we have a road here which is connected to a heat source and which is maintaining it at 100 degrees Celsius. And towards the other end of the road, it is like towards the ambient temperature, otherwise it is towards the atmosphere. And that end of the road is fixed at 25 degrees Celsius. So here what we have is at the starting and the end of the road, we have like two conditions to be satisfied. And here we have it's a second order ODE. So the first thing we have to convert, so the first idea what we have is whenever we have a second order ODE, we need to first convert into two first order ODEs. Okay, so that'll be the first thing that we have to do. Like first we'll have to divide this two second order ODE into two first order ODEs. Okay, and later we'll try to see how to implement this boundary value conditions. Okay, so now moving forward. So this is how it has been done in a Matlab solver which is called as BVP5C. So BVP5C is an inbuilt Matlab solver. Like for ODE, IVP, we had solvers like ODE 45, ODE 15S. You remember stiff and non-stiff problems? So here this is a solver for ODE BVP problems. So here first what we have to do is we have to convert this into two first order ODEs. So for that what do you do is like we used to do before. Let's say that dt by dz is a new variable which is y, small letter y. Okay. And then you say dy by dz which will be nothing but it will be d square t by dz square, which is nothing but what is given to you in the question, that is gamma t minus 25. Right? So here we have two equations. One is this, the other one is this. So what you have to do is we have to define another variable which is capital Y. And you say that in capital Y has two variables which will be this and this. So the first variable is t and the second variable is small letter y. And what do you do when you say d of capital Y by d of dt? It will be nothing but it will be d of t by, sorry, the by is not there. Okay. D of small y, which will be a column vector, and this will be equal to what? It will be equal to the two functions. So what will be the two functions? It will be, sorry, it will be d by dt. One d by dt I missed here. Okay. And what is dt by d? The temperature, sorry, d here it is not time. Here it can be both time also, but in this question we have it is better based on distances. So it should be z here and z here. Okay. So here what do you have it in the first equation? The first equation will be this part, that is y. And the second dy by dz will be nothing but gamma t minus z. T minus 25. Okay. So this is what we have. Is this part clear to you or should I explain it again?
Clear,
So
ma'am.
finally what we'll have is we'll have an equation like this. D capital Y by dz will be equal to d by dz of a column vector which has time, sorry, here it is temperature and small letter y. And here we have dt by dz to be equal to small letter y. and dy by dz is nothing but gamma t minus 25. Okay, so this is what we start with. So here what we have, we declare a y. What is the BC here? BC is the boundary condition. So what I said is earlier I showed you the road, right? We had a road like this. Okay, when we had the ODE IBP problem, so what we had is at z equal to 0, that is you're calculating the length of the road. Okay, length is starting from here, so this is where the length is starting from, this is where z is equal to 0, and this is where z is equal to, for example, let us assume that the road length is L. Then the boundary condition means we have a condition at the starting of the road and the ending of the road. So the starting condition is at the starting of the road at z equal to 0, the temperature is 100 degrees Celsius. And at the end of the road, the temperature is 25 degrees Celsius, which means you have the temperatures at the two boundaries. So this is called as boundary value condition and this is called as a BC. I'll come to that later. Here, what is BC? I'll come to that. So first we have declared capital Y, which is a column vector of t and small y, this part. And then we have dt by dz equal to y and dy by dz is equal to gamma t minus Ta. Okay, here this I'm just calling it a new variable Ta, ambient temperature. Okay, that's it. Now we need to know how to incorporate this boundary condition. Okay, so in BVP 5C solver, how do we include this boundary condition is you write it in a form of a function. Okay, so what happens is you have to write it in a form of G uh, T my, okay, do I have a, just a second. Yeah, yeah. So here what we do is we write it as a function equal to 0. So how do you write it as a function? You know that t z equal to 0 is equal to 100, right? So let's bring the 100 towards this side. So that will be t z equal to 0 minus 100 is equal to 0. And similarly, we'll do the for the next boundary t z equal to L minus 25 is equal to 0. Okay, we have to write a function like it is equating it to 0. It should be like that. The right hand side should be 0. So these are the two functions. Now we need to know how to code this function, which I'll tell you. So one, okay, maybe here itself I'll tell you 1 second. So how to code this one is like, you know, this is time, this is time, sorry, this is temperature at z is equal to 0 and this is temperature at z equal to L. Okay, remember your y. Okay, y has, what all does y have? Y has the temperature and it has a small letter y, right? This is what the y had. And imagine you have the road here. Okay, and then this position will have a temperature and y is what? Y is derivative of temperature. So here you will have y0, which will have t0 and v0. Another point we will have y1, depending on you can divide the whole thing into grid. Okay, I am dividing this into grid like this. So what happens is this will have y1, this will have y2, y3, y4, y5, and this is y6 if I'm dividing it into 5 intervals, right? So let us take this y0. Okay, y0 what will have? Y0 it will have two values like this, which is t0 and y0. Okay, and let us talk about y, the last here what it is, y6. Y6 is having t6 and y6. Okay, out of which what all information you have, out of which you know what is t0. T0 is has to be 100, right? T0 has to be 100, that is what is given here. T0 has to be 100, this we know. And we know what is t6. T6 is the temperature at this point, that is given to be 25. So we know this value and this value, right? So how do we declare it is in such a way that, just a second. So how do we declare it is such a way that we'll write a y. We'll come to this in detail while we are coding, but we'll say that in y there are two entries, one is t0 and y0, but in that we'll say the first entry. Okay, let the first entry be equal to, that is first row first column. Okay, first row first column be equal to 100, or else you can write y, when you're writing as a function, it will become minus 100 is equal to 0. And the last one is y6. Y6 means, so this is y0 and y6, first row, first column minus 25 is equal to 0. This will be the way you'll be coding it. I know it's a bit confusing, but we'll come to that. Okay. So for BVP5C, what you need is, first you need to have the variables in this y vector. You need to have the ordinary differential equations like this, and then you need to have a function for accommodating the boundary conditions. So these are the things we need to define the ODE, okay, and we need to define the BCs. Okay, now let us discuss by looking at the code. Just a second, just give me some time. Let me just share Matlab. Can you see Matlab? So here what we have is, we have certain parameters given to you. Gamma is this parameter, okay? This parameter is given, gamma is equal to 4. It is given to you in the question. TA is the ambient temperature, which is given as 25. And what you have is L. The total length of the road is taken to be 1. These things are given to you in the question. Now next thing what you have to notice it, the whole thing is divided into 10 intervals, okay? N is equal to 10. And so how many, what will be my step size of each interval? You know how to do it, right? So h is equal to the total length divided by n. You'll be getting the step size. So now what you can do, you can divide z as starting from 0 and with the step size of L by n till the total length, which is 1. Okay. So here it will be 0 with h and L. Okay, that's what we write here. 0, L by n is h, and length is 1. Okay. Now what we have is, we have to declare. We have to have a, we'll come to this initialization 1 minute. We'll come to that. So first let us go here. So this is the normal syntax of BVP5C. So we have a solution vector. What will the solution have? Solution will have at this all the grid points. If you're dividing like a road like this, just a second. Okay. If you're dividing a road like this, at every interval, what is t, what is y, what is t, what is y, this will be the solution. This will be the y solve, what you will be getting. Okay, this will be the y solve. So we'll have a solution vector. So this is y solve, and this is the for general keyword BBP5C. And then you need to have a function for defining your ODE. This part we did for the ODE IVP problems also. Okay, and then extra one thing is that we need to have a function for the boundary conditions, and this is the initial values. This initial value was there for ODE IVP also, but there's a different way in which we initialize it. So we'll come to that. So first let us look at the this ODE function. So which is ODEs are written in the function ODE FCN. Let me open that. Okay. In ODE FCN, what happens? It will take in y. Y is the capital Y, and all the other parameters, that is gamma, the length, and all the parameters will be taken. And out of y, you know, y contains 2 entries, right? So the capital Y has 2 entries, which is temperature and small letter y. So you need to extract from the capital Y. So I'm telling the first entry of y is temperature, and the second entry of y is small y, which is dt by dz. Then what I do, I have to write a just a second. Yeah. So the capital Y has both T and Y, which we extracted. Now we need to write a column of the functions, just like we did for ODEs. So what do you do? This function, this column vector, I'm calling in this code as dy dz. Okay. In that, the first entry will be, what will be the entry? It will be corresponding to dt by dz, whatever it is. That is y. Okay. And the second entry is for dy by dz, which is nothing but gamma t minus ta. Oh, so that is this. This is the first function. This is the second function. And what do we output? We output this column vector. Okay, this column vector is outputted here. Any doubts so far? Any doubts?
No, ma'am.
Okay. Is there any disturbance like in the noise disturbance or anything?
No, ma'am, nothing like that.
Okay, sorry. So yeah. So right now we have written the function like this. Now what we have to do is, let me go back. So now going back to the rod conduction problem. Here we have the uh, equations here. Next is we need to define how the boundary conditions are. So for that, the boundary conditions are written in this problem, that is rod in this code rod BC. Rod BC takes in two variables, y0 and y1. You can give any other variable name also, that is completely fine. Y0 is for the initial boundary, y1 is for the last boundary. Okay. Earlier when I was writing in the PPT, it was y0 and y6. Okay, it's your wish. You can give any variable name. It's completely fine. So here what I did is it was y0 and y1 is the input. Y0 is for the first boundary and y1 is for the second boundary. And you have to write it in form of a function. So as I said earlier, capital Y0 has two entries. That is capital T0 and small y0. And this is for this end of the road. Okay, here this one is having y0 and this one has y1 according to my, sorry, this one has y1 according to my code. Okay, so y0 here has t0 and y0, and this I say this value was equal to 100. So how do I write? I write y0, this is the first row and this is the first column, minus 100. Okay, and this one is a function, and this one function I write it. Ma'am, please display the problem statement. Just a second, is just Hi. So just can anybody let me know that there is a problem with my voice? So there's a lot of disturbance. Is it audible or is there any disturbance in my voice? Can somebody let me know that in the chat box? Is there any background noise coming or is it okay? No disturbance. Okay, fine. Good. Okay. Thank you. So what we have is we have the first boundary condition, that is T0 is equal to 100. So what I write, this is Y0's first row, first column, that I write it as 100, and this is the function, right? So this one I write it in a column vector. Okay, this is the first value in the column vector. In the second value of the column vector, I write the second boundary condition. That is, this is y1, right? This value here, it is y1. In that also, y1 will have what all? Y1 has, it has t1 and y1. Okay, in this I know what is this value, which is 25. So this one I write it as like in T1. T1 is what? T1 is Y1's first row, first column, right? First row, first column minus 25. This I write as a second function, and this whole function I am calling it as residual. Okay, so this is like I can give it by any variable name, that is completely fine. So here I am just calling it as RES, and RES, it has one. So sorry, not this. Yeah, I'm calling this as Megasri. If you don't have any questions, please do unmute yourself. Please mute yourself. Yeah, thanks. So this is what REST does. In REST has one column and two entries. The first row will be the first boundary condition, and the second row will be the second boundary condition. Do you have any doubts regarding why is it is y0, comma 1 and why is y1, comma 1? Any doubts regarding that? See here, while explaining, I have written as 1, 1 comma 1 and 1 comma 1. Okay, that is not necessary because it just means that it is only having one entry, right? So you can directly, so since y0 is a, so what I'm meaning is here y0 y0 is a single column vector, okay, which is having t0 and y0. If you write y0 1, it means it is d0, or y0 1 comma 1 also, it means it is d0. Okay, just means is that you have to extract this entry. Okay, is this clear to you, this boundary conditions? This is very important. Okay, that is why I'm asking you again and again. Okay, I hope everybody understood. So let me just go back. So here we have the equation, here we have the differential equation that is saved, and here we have the boundary conditions that is saved. Here, why do we write here z and y? Because in this function you have, it is dy by dz. Okay, so these are the variables. That is why I write here at the rate y and z. And here the variables are y0 and y1. So that is why I write here y0 and y1. Now next important is we need to give the initial guess. Okay, so here BVP5C uses a small trick to give the initial guess. So what I do is, every solver needs an initial guess. Okay, that we have seen so far in Matlab. So what do we do is, let the road be like this, and you're dividing the road to be final grid. Okay, so what I consider is, I'll consider the every roads, every position, every grid position to have a single initial guess. So that's what I do. What I say is, let here the temperature be 50, here the temperature be 50, here the temperature be 50, 50, 50, 50, 50. Okay, and my y, which is d dash dt by d dash. So here I'm taking it to be minus 50. I'm just considering as minus 50. Okay, this is just a random initial value that I give based on my experience. So this is minus 50. This is how I initialize. Now what happens? The solver, as it starts to solve, this value will be shifting. This grid value will be shifting to something else. It will be shifting to 100, 20, something like that. This will be shifting to maybe 90, 10, something like that. It will keep on shifting. Okay. But first, this grid needs a starting point. So that starting point, what I say is, at every grid point, I'll decide a single temperature. At every grid point, I'll decide a single y value, that is dt by dz. So this is what I do. So instead of, so how do we code this? Okay. So to coding that, you have a function which is called as bvp int. So let's look at help. BVP5C. I don't know. Oh, yeah. So BVP5C, we'll have an ordinary function, ordinary differential equation function, then the BC function, that is for the boundary condition, and then you have the solution initialization. Okay, so for the solution initialization, what do we have is it given here? Just a second. Yeah, for solution initialization, we have a function which is called as BVP int. Okay, so we'll look at, yeah, ma'am, will you be able to access Matlab in exam? Okay, you didn't get answer for this question in your Google forum. Now, as far as my knowledge, you will not have access to Matlab. Okay. And I had another question from somebody, like, will the problem statements be displayed? Yeah, of course, I'll be sharing this PPT to you after the session. Okay, so whatever is there in the PPT, you don't have to note it down or anything. The PPT will be shared to you, but the codes will not be shared to you. Okay, whatever the codes I'm sharing will not be shared to you. For that, what I'll do is I'll be sending the recording of this meeting later, not today, maybe tomorrow. So then you can just pause and take a screenshot of the recording. Because if I give you straight away the codes, you will just copy paste it. But the PPTs, which will have the questions and everything, will be shared to you. Okay. So now let's go to BVP int. So in BVP int, what you have to give us input is first the grid points. Okay, this is the positions. Positions is what? It is 0 to L with a step size of H. So these are the positions. And the second input should be what should be my initial value. So I give the BVP int, I'll give this as the input. I'll give you the grid points. Okay, that is the Z values I'll give. Okay. And then what I'll give is the a column vector like this, which will have 50 minus 50. So what will happen when I run it, it will have this, and this portion will have 50 minus 50. This will also have 50 minus 50. Every point will have 50 minus 50, where 50 will be for the first variable, that is the temperature, and this will be for the second variable, which is small letter y. Is this clear? That will be automatically done by the BVP int. You don't have to worry about it. So I hope everybody have understood so far. I'll just run and show to you what will happen. Okay. See. So this is the total code in case you want to take a screenshot or something later. So now what we do is, I'll run this show you. Okay, I'll run this for you. It'll take some time. Just wait. It'll take some time. So this is what you'll be getting as a plot. So now let us look at each of the things. So what will the Z value is? So Z value, you know, the length is from 0 to length is 1, right? So the Z value goes from 0, 0 0.1, 0 0.2, 0 0.3, 0 0.5, 0 0.7 up to 1. Okay. So that will be the last Z value, which is 1. So we have understood that. Now let us look at what will be this Y initial value. Will it be as I said before? Okay. Y initial value is a structure in Matlab, but let's look at what all will be there in Y initial value. First, this will have the grid points. Okay, this will be the grid points. That is 0 to 1. Okay, now going back to Y in, let us look this. What is Y we're giving you? So you see, this is what I said. Corresponding to every grid point, you will have 50 minus 50, 50 minus 50, 50 minus 50, so on. So there are 11 entries in Z. So here there are 11 entries for the Y values. So this is how BVP int will initialize your problem. Okay, you don't have to do anything. All this arrangement will be done by the will be done by the function itself. So now finally, as this is there, we'll run the solution and let us look how this VSOL looks like. VSOL will also look like this. In VSOL, it is also a structure. I hope that by this time you know how to access structure. So if you need to see what the X value is of a structure, so let's write the structure name here, VSOL. And if you want to extract the X values, you just put a dot and X value, you will get the X values. See? And if you want to get the y values, you'll just print y sol dot small y. You will be getting the y values. So let's look at the y values more closely. I'll just click it here. See, and the y values will be like this. So here, if you want, you can cross check two things. This first entry is what? The first entry is y0, right? This is y0. This is y0. And you know in the y0, the first is t0. Y0, what all it has? It has t0 and small y0. And this is what? 100. That was given to you in the question. After solution, just check, is it 100? Yes, it is 100. Okay. So the boundary condition has been properly placed, and after solution also it is there 100 itself. So this is correct. Now let us go back to the last entry. Let's to check here. See this entry here. So what was this? This was y1, and which had two entries, that is t1 and y1, and this we know was 25. After the solving, is it 25 itself? Yes, it is 25 itself, right? So this is how you check your boundary conditions. So the boundary conditions has been properly applied here, and we have got the solution. Now, if you want to plot, so here I am only bothered about the temperature. So what I do is I extract the temperature alone. Or how do I extract? I extract y sol. In that y, when I extract, I'll get both. Okay, y sol, y has both temperature and small letter y, right? The first row is the temperature. The first row is the temperature, and the second row is the small letter y. I'm only worried about the first row, which is temperature. So what I do, I take y sol dot y. In that, the first row, all columns. This will give me the temperatures. That is the t sol. Okay. And then I plot it. Y sol dot x will give me the grid points, and the corresponding temperatures will be plotted here. And then I'll get it like this. Again, here in the graph also, you can check at one end of the road, the temperature is 100, and the other end of the road, the temperature is 25. Is this clear? Any more doubts? Any doubts?
Ma'am, at every point of the rod, why do we take that 50 and minus 50, ma'am? That I did not understand. Can you explain it?
It could be any value. It need not be 50 and minus 50. What happens is, this is the solver, no? The solver, this is what it does. The solver, it needs, it automatically, it works on grids. Okay, that you understood, right? The solver needs grid values. And for the solver to start with, it need an initial value of temperature, and it need an initial value of temperature and y at all points. That is how that solver needs starts. So what happens is, I'm just giving, see, the value is here 100 and 25, right? So you know one end of the road is 100, other end of the road is 25. So the bottle, by just by common sense, what do you understand? So the mid of the road should be, the temperature should be somewhere between 100 and 25, right? That's how physically it happens, because one end of the road is 100, other end of the road is 25, which means there is a, technically there is like a gradual drop of temperature from 100 to 25. So what I do is I just take something in middle, that is 50, and I say that let's take start from 50 here in all the grid points. Okay. And dt by dy also, that is also a guess only. I'm saying, okay, what I think is, my temperature is dropping, right? Which means it is a negative gradient. Okay, negative gradient means something is minimizing. Positive gradient means something is increasing. So I just give a negative value. I can give any other value, negative 10 or something. I'm just giving negative 50. Okay. Now the BVP5C, what happens is, BVP5C works on grid, and it requires some initial values to be defined at the grid points. Okay. So this is different from what we did in ODE IVP. In ODE IVP, you only needed a guess for the starting. Okay, rest it used to build from here. It used to, from this value, you will generate this value. From this, you will generate this value. This, you will generate this value. It happened like that. Okay, we went from the first point to the starting point. But what happened in BVP5C is, it begins together. All the grid points are started together, and then as time progresses, it is evolved together. Okay, so that is why you need to have a entry for all the grid points in the beginning itself.
Yes, ma'am. Yes, ma'am.
Okay.
Understood.
Yeah. So that's about BVP5C solver. Now let's go to the traditional method, that is finite difference method. So in finite difference method, let's see how to solve this problem. Okay, the previous problem that we had. That is d square t by dz square gamma t minus 25. So you know this is a second order differential equation. So using finite difference, we also know how to, in finite difference, what the formula is. So every second order function can be written at a point zi can be written as f of xi plus 1 minus 2 times f of xi plus f of xi minus 1 divided by h square. This is the second derivative central difference formula, which we have seen already. So now what we do is we try to create a matrix like this. Okay, we try to create a matrix like this. Okay, so matrix probably it will be like a tridiagonal matrix. You will understand while we are solving. We'll end up getting a tridiagonal matrix like this. What is tridiagonal? If the curve increases from 25 to 100, then the value y value will be positive. Yes, yes, it will be positive. Yeah. Sharon, yeah, that's the answer for your question. It's just let's give some guess that is closely matching to what is happening physically. So if the temperature was increasing from 25 to 100, it means there is a positive change in temperature, which will be a positive gradient. So you have to give a small letter y initial guess to be something a positive value. Okay. Even if you give negative value, the solver might find it. It depends on how bad your guess is. Okay. Sometimes in some cases, even if you give a bad guess, the solver can get you an answer. Okay. So now here what we are getting is we'll be getting a tridiagonal matrix like this. What is a tridiagonal matrix? It'll have the main diagonal d1, d2 up to dn. It'll have an upper diagonal that is u1, u2 up to un minus 1. It'll have a lower diagonal that is starting from L2 to NN. So this is the A matrix. Then you'll have a constant vector that is B, and this is your variable vector. So how will you have it? You will have it in a form. Just a second. Um, Yeah. You will have it in a form A, Y is equal to B, and here Y will have the temperatures T1, T2 up to Tn. In this, you will know, since the boundary value is given to you, you know what is T1. T1 is the first boundary temperature. Tn plus 1 is the last boundary temperature. You will know all this. When you solve this, what you will have, you will get T2 to Tn. So you how do you solve it? It will be inverse of A multiplied by B, and this B will have all the temperatures, all temperatures. Okay. Likewise, you will get what will be the temperature as intermediate points. Okay, this is how we solve it. Now let's look specifically to this problem. What is A, B, and Y? So this is the question d square t by dz square is equal to gamma t minus 25. Let's divide the whole road into grids starting from t1, t2, t3 up to tn plus 1. That is n intervals means n grid points. And t1, the starting end of the road t1 is 100 and the other end of the road tn plus 1 is 25. Okay, this info is given to you. Now let us write for this part of the equation, let us divide it by the central difference formula. So this part you already know. So we have to start from this part. So T1 we already know that is 100. For this, let us write the central difference formula. So how do you write? At the second point, okay? At second point, it will be T3 minus 2T2 plus T1, right? Has to be divided by h square is equal to gamma T2 minus TA. Is there anybody who haven't understood this formula? This is a central difference formula f of xi plus 1 minus 2 times f of xi plus f of xi minus 1. I am writing it for the second grid point. Divided by h square is equal to gamma T2, which is the temperature of the second grid point, minus TA. That is 25. Okay, any doubts in this expansion? Okay, now what do you do is you have to take the h square to the other side. So it will become T3 minus 2T2 plus T1 equal to h square gamma T2 minus TA. That is this equation. Okay. Similarly, you can write here also central difference formula. So what will it be? It will be T4 minus 2T3 plus T2 divided by h square is equal to gamma T3 minus TA. We can take the h square to the other side. So like this, you will have to write the central difference formula till Tn minus 1. Till Tn minus 1, you will have to write the central difference formula. Sorry, Tn. It is not Tn minus 1. I think it's still Tn, right? Yeah. So you'll have to write central difference formula from T2 to Tn. How do you write for Tn? Tn, it will be Tn plus 1 minus 2Tn plus Tn minus 1 divided by h square will be equal to gamma Tn minus Ta. Is this clear? So this will be the formula. This will be the for the second grid. Okay. Similarly, you will have, so this will be the general formula for the ith grid. Ith grid, you will have Ti plus 1 minus 2Ti, Ti minus 1 divided by h square will go to the other side. Then gamma Ti minus Ta. Okay. This will be for the nth grid. N plus 1th grid is this. N plus 1th grid is this. This is the first grid. Is this clear? Any doubt? I hope there is no.
No, ma'am.
Now what we have to do is we have to create it in the form of a matrix. So here we know the vector. This vector we know. This vector has T1, T2 up to Tn plus 1, right? And here we have a vector, a B vector. This is Y, this is B, and this is your vector A. Okay, let's write the first equation. First equation is this. Okay, what is the coefficient of T1? It is just 1. And then there is no equation, no entries. Okay, so there is everything is 0. You know, when you multiply this matrix, T1 is equal to 100. So 100 should come here. Okay, I hope it is clear. Next is we write the second equation, that is this. So at the position of T1, the coefficient is 1. Okay, at the position of T2, the coefficient is minus 2. At the position of T3, the coefficient is again 1. Rest everything is 0. And what should be the other side, the B part of the equation? So when you multiply, it will be T1 minus 2T2 T3 is equal to h square gamma T2 minus T1. So it will have h square gamma T2 minus Ta. That will be the second entry. And the next, if you're writing the T3 equation, I'll just write one more equation just for understanding. So it will be T4 minus 3T2 T3, sorry, plus T2 is equal to gamma square h square gamma T3 minus Ta. So how will you enter this? You don't have T1 here, so this will be 0. T2 you have, so the coefficient is 1 here. T3 the coefficient is, sorry, T3 the coefficient is again minus 2. T4 the coefficient is 1 here. So again 1. And rest all are zeros. And what will you have here? You'll again have h square gamma T3 minus Ta. And finally, you'll have all the equations. And finally, final equation will be Tn plus 1. Here the coefficient is 1. So you'll have 1 here. And here you will have 25. Is this clear how this matrix has been formed? Any doubts?
No, ma'am, no doubt.
Yeah. So now you can see that this matrix has a lot of zeros. So basically, this will be your main diagonal. This will be your upper diagonal. And this is your lower diagonal. That is why I said it looks like a tridiagonal matrix for this problem. Now what we'll have is you'll have to generate this one, this matrix, and simply y will be nothing but inverse of A multiplied by B. It is pretty straightforward. So let's try to do that in Matlab. So this is how you start the problem. So initial parameters, which is the gamma value is equal to 4. Ta, that is the temperature, which is 25 in the question. That total length of the road is 1. And dividing the road into 10 intervals. So each h will be L divided by n. This is my grid points for the position 0 with the step size of h till I reach L. Now I have a matrix. So initially A matrix I'm declaring all to be zeros. Okay. So there are n plus 1, as I said earlier. Am I not sharing it? Oh, sorry, Lukush. Yeah, I'll go through it once again. Gamma is equal to 4, TA is equal to 25, length of the road is 1, and we are dividing it into 10 intervals. Each interval will be L by N length. So the total HZ grid point will be 0 with a step size of H till I reach L. Okay. Now what I do is I declare the A matrix. First I'm declaring it to be zeros. How many zeros it will have? There are n plus 1 grid points, right? So there are n plus 1 grid points. So my A will be n plus 1 cross n plus 1. It will have n plus 1 rows and n plus 1 columns. So that is why I write 0, n plus 1, n plus 1. It will create a matrix full 0 entry. And B also I am declaring it will have n plus 1 rows and 1 column to be all zeros. Now what I do, I have to start building my A matrix. For starting building this A matrix, I am telling let A11, which is the first entry of the matrix, to be 1, and the B vector's first entry to be 100. Okay, because this will be equal to telling you T1 is equal to 100. Okay, that is what this is doing. So that will be this equation. Now we will have to build the internal points. So for that we are running a for loop where I goes from 2 to n. 2 means it is for the row number. Okay. So now the first, as you remember, the first row was like this. Okay, the first row is done. This part is done. Now let us look at the second row. So here we'll go from I equal to 2 to n. 2 to n, because the last row, this is also 1. Okay, so we'll run from 2 to n row. And what all will you do? You will say I11 means the main diagonal, right? If you look at the main diagonal, it was of the form minus 2 h square gamma. That was a main diagonal entry. This is the comma I minus 1 is what? This is, so if you're taking I equal to 2, this entry will be I is equal to 2 and I minus 1 is 1. What is 2 comma 1? That is second row, first column. Okay, that is this. So this portion is what? This is the lower diagonal. And the lower diagonal also we knew it was 1 was the entry. Now next is, this is what? This is the A. I comma I plus 1 is nothing but your upper diagonal. And in our question, we know that is also equal to 1. Okay, and this is the main diagonal. So this is how we build it. So when in the first loop, first row will be, the one row will be filled, and then you go to the next row and so on, it will be done. And BI, what will happen? In BI, the entry is minus h square gamma TA. This will be your entry. So once this loop is run, you will have all the rows except the last row. Now this is how we build the last row. I'm telling the last entry of the matrix, that is A n plus 1 comma n plus 1 should be 1. And the B's last entry should be 25. This is nothing but I'm telling A T n plus 1 is equal to 25. This is my right boundary condition. Okay. So now I'll just show you all the, just a second. So now I'll just run and show you. Once you've created the A matrix and the B matrix, the temperature is nothing but inverse of A multiplied by B. I've always told you there is another way to calculate inverse. That is, just a second. Yeah. A backslash B is equivalent to inverse of A multiplied by B. Both are the same. Okay. A backslash B. So I'll just run this. You get the same plot as we got earlier. Now let us look at the A matrix. Okay, A matrix looks like this. The first row only has 1, then everything is zeros. Second row has 1, minus 2.041. Then again, this is a tridiagonal matrix. As you see, this is your main diagonal. And this is your lower diagonal and this is your upper diagonal. Okay, you've got your 3 diagonals. So this is a tridiagonal matrix A. And what will be your B? I'll just open B also. So B is a row vector. The first entry will be 100, last entry will be 25. Rest of the entry will be there according to the formula. Okay. Now let us look at the temperature. So we know the temperature is in the variable T. After solving, the temperature will be like this. At the starting point, the temperature is 100, last point temperature is 25. And here you will see there is a smooth fall between 100 to 25. So 100, it goes from 85, 74, 64, and finally it will become 25. So if you want to plot, how do you plot it? So here I'm plotting it with Z, the position and time. So I'll get the same plot as I got earlier. In the plot also you can see the starting value is 100 and the last value is 25. Is this clear how to solve using finite grid?
Yes, ma'am.
Yeah. Okay. Now let us
Yes,
move on.
ma'am.
Yeah. Okay, fine. I'll move on to the next. Next is a shooting method. So this is like a what you say, like a trial and error kind of a method. Okay, you start with an initial guess and you keep improving your guess. So that's what we do here. So what the main idea of shooting method is, we know how to solve ODE IVP problems. So solving ODE IVP problems, we have lot of solvers like ODE 45, ODE 23s, ODE 15s. There are a lot of solvers which we have already covered. So why not convert this ordinary boundary value problem to an ordinary IVP problem? So the idea is convert an ODE BVP problem, an ODE BVP problem to ODE IVP problem. How do we do that? In ODE BVP problem, we have two boundary condition. In ODE IVP problem, you need initial condition. That is at z equal to 0. Because it's a second derivative, you need two conditions. So at z equal to 0, you need to know what is t. And we also need to know what is t dash. If you know this, then this question will become an ordinary IVP problem. Okay. Here what we know is at z equal to 0, we know t. At z equal to L, we know t. This is the BVP problem. So how do we convert this into this? Sorry. So for converting this, what we say is that in this question, we don't know what is t dash at z equal to 0. That information is not with us. We only know what is t at z equal to 0. So we first assume a value for t dash. Let's assume a value for t dash and let us solve the ordinary differential equation, ODE IVP problem, using the traditional ODE solvers we have. And then what we do is, when you solve the t dash, what will happen? You will be getting the temperature as at all points. Okay, you'll be getting a T salt, right? When you solve using ODE VP problem, you'll be getting a T salt. What will be the end value of T salt? End value of T salt will be nothing but the at the last grid point what the temperature is. Okay, T salt end will be the temperature at this point. Let us see if this is equal to what is given in the question. If this is equal to 25, okay, fine. Then the smooth gradation is correct. If it is not equal to 25, we'll improve this guess. This guess will be improved. Okay, so this is like a chain procedure. First, you will have this guess. We'll solve the ODE and then we'll see what is the value at the endpoint. If the value is wrong, we'll improve this guess, again solve ODE, and we'll check if it is 25. So this is like a loop. Guess the value for TDS, solve the ODE, check the residual. Residual means you have to check what is the actual boundary condition, that is 25, and what is the solution you're getting from the ODE solver. If this is exactly matching, it is fine. If it is not matching well, then you improve the guess and you go through this loop again. Okay, this shooting method is not a very convenient method, but this is one way you can solve it. Okay, we'll go through that. So let me just take Matlab. So at starting, we have the gamma value to be equal to 4 and the TA value to be equal to 25. The length of the road is 1. I'm dividing into 10 intervals. So each interval will have L by N gap. So now this is my initial guess. Okay, initial guess of temperature. This is given to me in the question. This I know already. So T0 is equal to 100 and the y value I don't know. So this is basically, just a second. So this is basically for Z equal to 0. Temperature I know, which is 100. Okay, this is given to me in the question. Now I don't know what is y value. That is dt by dz, I don't know. I'm just assuming it to be minus 50. This is what I gave as initial guess, right? For the BVP5C. I'm just randomly taking it as minus 50. Now what I do is, this is what I'm getting it as minus 50. Then I make this as an initial guess. So my initial guess comes like this, 100, comma, minus 50. Okay. Now what I do is, I have my set span. If you remember, this was the syntax for ODE BVP. You have the Z sol and corresponding Y sol. You call the ODE 45. You have a boundary condition function. So this I'll take again. This is like this. It'll have Y. In that you should extract the first Y value to be temperature, second Y value to be dt by ds, which is the slope. And then this is the first function. dt by dz is equal to Y, and dy by dz is nothing but gamma t minus ta. Okay, so this comes as the output here. So same function that we used earlier. So this is road function. Set span is the grid that I'm using. So this is the grid I have. Okay, 0 to L with the step size of h. And this is my initial condition. Initial condition will have this 100 and minus 50 to begin with. Now, when I run this solver, I'll be getting for every z what is the y sol. And that y sol will have both t and y. So let me run this. So when I run the first section, solver is running. Okay, I get something like this. So this is my y sol and this is my z sol. My set sol is from 0 to 1. You can see 0, 0 0.1, 0 0.2. The grid is still 1. And y sol will have two solutions. So the first column is for, this is the initial value that I gave for temperature. Okay. This is temperature and this is small letter y. It starts from 100 and it's dropped to 219, 216. And this minus 50 to 355. So now this is at z equal to 0, right? And this value will be for z equal to 1. And using this solution, I am getting z equal to 1 value to be 2.64932. It is not equal to 25. Okay, it's not equal to 25. So how do I check it in code? So what I can do is, I already got y sol. From that, I extract what is the temperature. That is the first column. That is all rows first column. So all rows first column, I extract the temperature. Okay. Then I see what is the last temperature. That is T sol end. And you subtract it from 25. You can do other way also. That is 25 minus T sol end or T sol minus 25. Both are possible. That is my residual. That difference is my residual. And I'm plotting. What am I plotting? So my plot went somewhere else. So just a second. I'll just run this code again. So this is the kind of plot I'm getting. At the beginning, the temperature is 100, but at the last, my temperature is 216. This is not the right thing. So with the guess of minus 50, my residual is minus 191. Okay, residual is the difference between 25 and what I got from the solver. Now I'm improving the guess. So let me make it 450. Okay, and I'm again running this. I get a plot like this. So 1 minute, let me do one thing. I'll just I want everything to be on the same plot. So hold on. Clear. CLC. Minus 50. I run this. I get a plot like this. Now I make it as minus 450. I again run this. I get a plot like this. Okay, there is a, maybe I should add the legend also. Insert legend. Okay, so the data 2, that is for minus 450. I get it like a downward behavior. But again, my residual is large. So the idea is look for something that gives you a positive residual and a negative residual. Okay, the main idea is residual is a difference between 25 and what you get at the end. This ideally should go to 0. Okay, so here you have a negative residual and here you have a positive residual. Here I used minus 50 as a guess. Here I used minus 450 as a guess. So if I take something in between, okay, what is the between of minus 450 and minus 50? What is the value? Using midpoint formula, what will be the value? That is minus 450. Okay, 450. That is minus 250, right? So what I do is I give another guess, which is between this. That is minus 250. Okay. Again I run it. Now the residual has reduced. Okay. Now the residual has gone from 5. My largest positive residual was this. Now that has reduced to 171. So let me discard this point. I'll take this and this. So what is the midpoint of minus 250 and minus 50? I think that is 150, right? So I'll take 150 here. Okay. And again, I'll run this. I get a residual minus 10. So this is my closer to 0. So I discard this point. So then I check what is the midpoint of minus 250 and minus 50. So basically what happens is I started with a larger bracket. So I started with a larger bracket of minus 50 and yeah, I started with a larger bracket of minus 50 and minus 450. I am reducing this bracket and coming. Okay, that's what I do. So this you have to do a bit of trial. So when I'm using minus, now my next guess will be the midpoint of minus 250 and minus 150. So that is 200. Let me try 200. Running it again, the residual is 80. So this 171 I can cancel. I can avoid that. Now I'll take a different midpoint of this two. Minus 200 and minus 150. That I'll take minus 175. You have to go through this for a, if you want, you can write a code for this, okay? You don't have to do it manually. So 35, it is much more closer than 80. So I'll take 150 and minus 75. Midpoint of that is minus 162.5. Again running, I'll be getting 12, okay, which is again closer to 0. So I'll discard this. So I have minus 150 and minus 162. That is minus 156.25. Okay, now I get 1.1, which is okay, better than where we started from. So I'll take this one and I'll take this one. And I'm getting this one, minus 153.125 is my midpoint. So let me do that. And running it again, I'm getting minus 4. So now this is a closer match to 0. So I'll take these two intervals, okay? Minus 146.25 and minus 153.125. That my value is, I've already written here, calculated. So that is this value. Sorry, minus has to be there. I'm getting minus 1362. And you can keep on doing this, okay? Now I'll just close the figure and I'll run this again to show you how close the match is right now. Okay, now the last temperature that I'm getting is 26.63. Earlier it was a very high value. So you can see here also, Y-salt, the last temperature is 26.63. If you keep repeating it, you can bring it close to 25. Is this idea clear? Any doubts?
Ma'am,
No, ma'am.
want to add this
Yeah.
formula for initial guess where we can add, ma'am, in the program?
Okay. If you want to have an initial guess, I'll just a second. Just give me. So what you can do is you can put this whole thing till the residue. Okay, till the display part maybe. Though this whole thing in a loop. Okay, and in the loop we can have an if statement. Like if the residual is negative and compared to the maximum negative you have to have a variable that is having a maximum negative value. Just a second. It shouldn't be maximum negative value, right? Yeah, it should be the minimum positive value and it should be the maximum negative value. That will be your brackets, right? So you need to compare the residual, you need to compare, and you can replace these two variables. So this whole thing, that is from this y guess to this display part. This should come inside a loop. Is this clear? And you have to compare the magnitude, and you have to keep replacing this two variables. Okay, and for comparing, you can have this greater than symbol and less than or something you have to use, and then you can code it. You'll have to take some time and like you can code it. If you can do that, it will be much more useful. You'll have to not do it manually.
Okay, ma'am.
Yeah, okay.
Okay, ma'am.
So now for this, these are some variations to the ODE problem. We are not going to see how to solve this question, but I'll just tell you what will happen. Okay, how to handle these things. So now first, what if you have, earlier you had the function like this, right? Just a second. So the earlier function was d square t by dz square is equal to gamma t minus 25. So this was first order in terms of t. Okay, it was a linear function. This is a linear function. Okay, what if we have a non-linear function, something like t square or e raised to t or something like that? When you have a non-linear function, what do you do in this side? So you know that the boundary condition, nothing is going to change. So the BC, I'm talking about BVP 5C, okay? In BVP 5C, the function which had boundary condition, that will remain the same. The function for initialization, that is wherever we used BVP, INIT, that will also remain the same. But the only thing that is going to change is the ODE function. And how will it change? Let's go back to the Matlab. Okay. So this was a rod function, right? So this will remain the same as such because this is nothing but dt by dz. Okay, dt by dz will remain to be y only, but dy by dz, which is nothing but d square t by dz square, will be that non-linear function. For example, something like t square or something like e raised to t. So this part of the question will change. Okay, this part of the question will change in that case. Rest everything will remain the same. Is that clear? That is how you solve if you have a non-linear equation. Now going to the finite difference, what do you do? In finite difference, if you see, I'm going back here. Okay, the boundary conditions will remain the same. The first and the last entry is going to remain the same. But the only thing that is going to change is this. This will be changing, right? Instead of this, just a second. Just a second. Instead of this, now you will have a non-linear equation. Something like t raised to n or something like that. So where does this come in the equation? This comes here. Okay. This comes in your, it'll change where all? It'll change here and here. Okay. So whenever you're expanding your formula into the grid, you'll have to be sure of that. Okay. So here one problem will be there. Yeah. So this you'll have to try to solve it. If it is not possible to solve directly, you'll have to use a fsolve solver. Okay. For every equation, you'll have to use fsolve. Okay. You remember fsolve, you can go back. Fsolve is for solving non-linear equation. Okay. This will make this from grid point 2 to n. You will have a non-linear equation and that can be solved using fsolve. Okay. That becomes more complicated. So if such questions come, I prefer, like, I would recommend you to use BVP 5C itself. Okay. Now going to the next question, that is next kind of difference, that is Newman boundary conditions. So whatever we had here, we in the initial part. So just a second, I think I'm not sharing that. Okay. I hope you can see this. So here what happened in the initial part, we had temperatures at the both the ends, right? So we had here temperature at Z equal to 0 and temperature at Z equal to L. And this is called as Dirichlet boundary condition. Spelling is wrong. Yeah, NET. Okay, this is Dirichlet boundary condition. We have another boundary condition which is called the Newman boundary condition. Newman boundary condition, one end of the road you will have the temperature, the other end of the road you will have the TD dash, T dash, that is the gradient of temperature. Okay, when you have a mix of temperature and its gradient, it's called as the Newman boundary condition. So what will change here? Ordinary differential equation will remain the same, initialization will remain the same, but the boundary condition will change. And how will it change? So the boundary condition, what will happen? I'll just show you quickly. Let us go check the boundary function. This was the boundary function, right? So imagine I know what is the at Z equal to 0, I know the temperature at is equal to 100, let it be. At Z equal to L, I know what is T dash. So let it be, I'm assuming it to be like minus 50. Okay, time being. How do you write it? You know, here Y0 and Y1 two variables are there. Y0 has what? It has temperature and small y. And this is 100. This I don't know. And in Y1 also I have temperature. Sorry, I have temperature and I have y. This earlier I knew, but now I don't know. And this is equal to minus 50. So how do I code it? In my residual, this vector will be like this. Okay. Y0, 1 will be equal to 100. So I write this an equation like this. And in Y1, I don't know temperature. I know the second entry. So 2 will be equal to minus 50 will be plus 50. Okay, so this will change. Here, this value will change. This index has to be changed. So that is why I told you earlier, it is very important that you understand how this index works. The first index refers to the first variable. In our case, it is temperature. And the second variable corresponds to the second variable. In our case, it is small y. So in Newman boundary condition, if you are given a gradient value, you have to change this index value to 2. Okay, this will become 2 here. Is that clear? Any doubts? Okay. So if not, let us move on. So just a second. Okay. In finite difference approach, change in the right boundary condition apply central difference or backward difference. So here what will happen is, let me just go back. Okay. Instead of this, you will have a dt dash. So something like this. That is, we'll have t dash n plus 1 is equal to maybe minus 50. How do you accommodate this in the matrix? You can write a backward difference formula like this. That is t n plus 1 minus Tn divided by h is equal to minus 50. No, you have this formula, right? The backward difference formula. You can use a 2-point difference or a 3-point difference. And then what do? You can take the h to the other side. Tn plus 1 minus Tn is equal to minus h50. And this you can write it into the matrix. You have to just take the right coefficients. Okay, so when you have information like this, what you have to do is for this equation, you apply backward difference and then accommodate that into the formula. Accommodate that into the matrix. Is that clear? Which one? Which one should I explain? Is it the finite difference part, Sharon?
The one you explained back.
Yeah. So what I do is here instead of Tn plus 1, I know what is T dash n plus 1. This info is not there with me. But you know that my entire objective. Huh?
The previous one.
Oh, you want the okay. This one you understood?
No, you said that the backward difference formula, but I thinking of the previous one until.
Okay, just a second. I think you're thinking about sorry, you're thinking about this part?
Yes, ma'am.
Okay.
The one you explained in Mark.
Okay, so this one, what I'm trying to say is, earlier we had t, so this is y0. You remember in Matlab we had y0 and we had y1, which has which is t0, y0, that is t1, y1. Earlier when we coded, we knew this, we knew this. This was 100 and this was 25. Okay, so in our boundary condition, we knew that we have to write it in the form of a function. So what we wrote is, we wrote y0, which is this index, this is 1, right? This is index 1. You have to write it in a form of equation. That is, you have to equate it to 0. That is why how you write it in equation, right? So you bring this 100 to the other side, minus 100 is equal to 0. What does it mean? The first entry of y0 is 100. That is, t0 is equal to 100. This means t0 is equal to 100. How did you write y1? Y1 also temperature. T1, to get T1, you need to get first index. That was minus 25 is equal to 0. So this means that T1 is equal to 25. Did you understand this part?
Yes, ma'am.
Yeah. So this is how you write if you have the temperatures. Now, instead of this temperature, we don't have this information. Okay, this information is not with us. But instead, you are given T dash. What is T dash? T dash is dt by dz. What is that? That is y, right? So here given at z equal to L, y is equal to some constant. So I'm just taking this constant to be minus 50. Okay, I need some value. I'm just taking this to be minus 50. So now instead of this, I have this value. So this condition remains as such. This remains as such. But now I don't have this. Instead, I have in y1 the second index. That is this. Okay, that is equal to minus 50. So writing it as an equation, it will become bringing 50 to the other side, minus 50 plus 50 equal to 0. So here, if you compare this and this, the index change is the most important part. Here, this index said that I'm talking about temperature. Here, the index said that I'm talking about the gradient of temperature, that is 2. Okay, gradient of temperature, that is the given by the index 2. Is this clear?
Yes,
So,
ma'am. I got it.
yeah. So the here instead of 1, you'll have to write 2 and the corresponding value here. That's the only change you have to make. So that's about the ODE BBP part. I'll just give you some problems to solve and then we'll slowly discuss them. So as we used to do in the previous classes, I'll give you one problem. I'll give you a few minutes. And if you get the answer, please put it in the chat box and then we'll discuss. As I used to say before, like everybody, please put your effort to solving this question. Only then you will understand the difficulties you're facing. Okay. So this is the first question. If you have any doubts in the question, you can ask me. I'll give you 2-3 minutes and then we'll discuss.
Ma'am, does the syllabus does not cover any coupled equations to solve the boundary value problems, ma'am?
So this you're talking about coupled equations in the sense
Like non-linear equations, two or more
no no
equations?
no 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 no
No,
you
no.
might not have it. Yeah.
Okay.
Just go through what has been covered in the class. If you go through the recorded lectures, apart from this, there is a bonus material that is given to you, which is differential algebraic equation. That will also not be there for the exam. Okay, bonus materials will not be there for the exam. It's just if you want to know about it, yeah, you can go through it. So if I have time in this session, I'll cover that. Okay. Otherwise, you can just go through the recording lectures. That will be well enough. And if you have doubts, you can just put it in the forum or ask me in the next class. Okay. Yeah. Try to be well versed with the questions that we have in our assignments or whatever I'm sharing to you, because whatever questions I'm showing to you in my session are taken from the previous year assignments. Okay, so this will be the kind of questions you can expect. And I don't think you will have access to Matlab. So yeah, there will be a limitation to the kind of questions you can get. So yes, try solving this. I'll give you a few minutes and then we'll discuss the answer. Any answers for this question? Is anybody trying to solve it? Should I give you 2-3 minutes more? Yeah, let me begin answering this question. Okay, so here what we have is we have a second order BVP problem, and the equation is like this: y double dash plus y is equal to 0. So how does it come? Like you have here the equation. Just give me a second. So it is there a disturbance? So this is, so let's see, okay, it's with respect to x. So d square y by dx square plus y is equal to 0. So when you write it, it will be d square y by d x square is equal to minus y. So this will be the equation. So if you're writing it, how will be the first variable be? So let me just, I don't know what variable I use for writing the code. So let me just write it like z. Okay. Dy by d is x. I am calling it to be a new variable z. And dz by dx will be nothing but equal to minus y. Okay, so that is this. dz by dx means d square y by dx square. So this will be my two functions. What are my boundary conditions? Boundary condition is this. At both the point, I have y value, one equal to 0 and the other one is equal to 2. My length is from 0 to pi by 2. And this is my initial guess. Y initial guess is sin x and y dash initial guess is cos x. So we have to solve using BVP5C. Now let's do that. Just give me a second. So first I have to create an X mesh. So here I am going from 0 to pi by 2. I've only taken 5 grid points. Okay, you can create more also. That is completely fine. So this is my X value. Now I am initializing it. So initializing, what you should do, I should give the mesh value of the grid points. So that is given by X mesh. And here it is sin x cos x, right? I can either write it here directly. I cannot write it here directly because it is sin x cos x. So it is not a constant value. It is not like a constant value like we did before, like 50 minus 50. It depends on your mesh value. It is sin x cos x. So if your x value change, this will also change. So that is why I'm giving it as a function guess. So the guess function is being written here. Guess will take an input x value and the output will be a column vector sin x cos x. Okay, so x value from here, it will go here and you will get sin x cos x and that will be the output g. So that is what I give here. So that's what I give here. I'll be getting x mesh and the guess here. Okay, and if I want, I can just show you by running this. Just give me a second. I think just a second. I think I should also, I'll run it together and show you. Okay, that might be better. Now that is the boundary value condition. Now going to the BVP syntax, you need to have the BVP function. So that is being written here, the BVP function. It will take in x and y. Okay, in that, what should be I'm declaring it should be a column vector with all zeros initially. Okay, so first initially I'm just declaring it to be capital Y is there. Okay, if you remember how did we write it? dy by dx to be equal to z and dy dz by dx to be equal to y. So your capital Y will be y comma z, right? That is this variable and this variable. Now what will be your function? Your function will be this one. Z is what? Z is your capital Y second entry. That is y2, right? Capital Y second entry. And what is this? This is y, which is capital Y's first entry. So this will be your function. So that is why I'm writing it here. Okay. And sorry, there is a minus sign here. It will be minus. Okay. So your function is y2 and comma minus y1. This is your boundary value condition. Sorry, this is your OD equations. Now what we have is we need to have the boundary function. Boundary function, if you remember, one boundary function. In both the cases, we are given the y value itself. That is, capital Y will have y0 and y1. This will have small y and z, and this will have small y and z. Here it is equal to 0, and this one is equal to 2. So how do we write? Y1 first entry is equal to 0. Okay. And here y1 first entry minus 2 is equal to 0. Right? That will be the equations that we have. So y1 0 and y1 first entry minus 2. So this will be a boundary function. Is this clear how these three functions are written? This is for the ODE functions, this is for the boundary conditions, and this is for the initialization. So once you have all the three, we give to the VVP5C, you run it, you get the solution. Remember, in the solution, you will have two entries. One is the mesh, and you will have the y, in which the first entry will be small y, second entry will be z. So if you want to just plot how the y is changing, you will extract sol.x and plot sol.y, the first row. That will be the first y, only the y you are getting. Okay, I'll just clear it. Let me run the CNC. Okay, so this is how the sol int will look like. It'll have the grid, that is 0, 3. Okay, 5. This will be pi by 2. Okay, and now let us look at the initial values. Remember, it is sin x and cos x. So this is the sin, this is the cos x. Sin 0 is 0. Okay, cos 0 is 1. This is sin pi by 2, which is 1, and this is cos pi by 2. So that is how you get the initial values. Now let us look at the solution. This solution x will have the grid. Sol y will have two values. The first value, if you check, you can see the boundary value. This is y at 0 is 0. Y at the last entry point, last exit point is 2. Y at pi by 2 is equal to 2. That is matching exactly. So this will give you the y. So for plotting, what you do is you have to extract. I think I just plotted it. Just a second. This is how you get it. Okay, this will be the plot. This is x and this is y axis. And here at the starting, y is equal to 0. At the end, that is at pi by 2, the y value should be equal to 2. Okay, that is 2. Any doubts in this problem? How to solve this? Any doubts? If not, let us move to the next question. This is the next question. Again, I'll give you a few minutes to solve and then we'll discuss the answer. Okay. I shall discuss this right now. So, as we used to do earlier, let us see how this solver works. Okay, so this is with respect to x. So, d square y by dx square plus 2 by x dy by dx plus 1 by x raised to 4 y is equal to 0. Let me call dy by dx to be equal to z. So what I have is dz by dx plus 2 by x. What is dy by dx called? It is called as z, right? Plus 1 by x raised to 4 y is equal to 0. So dz by dx, I can take the whole thing to the other side. That is minus 2 by x z minus 1 by x raised to 4 y. So this will be my two equation. This is my first equation. This is my second equation. Okay. So now I have the boundary conditions here properly given to me. Okay. I initialize every point with 1 and 1. Both my y and dy by dx will be initialized by 1 and 1. Okay. And this is my analytical solution. I have to compare my solution to the actual solution that I get to this analytical results. So let me just share Matlab. First, I have the mesh from 1 by 3 pi to 1. I'm having 10 grid points. For initialization, I create the mesh and I have the initial guess directly given. I don't have to create a separate function and all because these are just straight away scalar quantities. So this is my BVP5C. I call the BVP5C. The function is given by here. Okay. So if you remember the function, it takes in x and y has two variables. Okay. So, so the first equation was dy by dx is equal to z. And as I said earlier, here this will have two variables. That one is z, one is y, the other one is z, right? So this will be nothing but your y's second entry. Okay, in this the variable is called as y. Don't get confused by the in the question y and the one which is used here. And the next will be dz by dx was given by minus uh, 2 by x z minus 1 by x raised to 4 y, right? So that will be minus 2 by x. Z is what? Z is the second entry. So that is y2 minus 1 by x raised to 4. Y is what? Y is the first entry. So y1. So that is what is written here. Minus 2 by x multiplied by y2 minus y1 divided by x raised to 4. Okay. And then you have the boundary condition. That is also pretty straightforward. The first boundary value is 1. The last boundary value is equal to sine 1. Okay, so that is the values here. Now I get the solution. Now I plot it. I plot the solution where the x plot. I have the x plot and the actual solution. Where do I plot? Just a second. Yeah. So here I have the analytical solution for both the y and y dash. So I need two plot. One is for the y and the other is for the y dash. So this is I plot x plot and in y plot I just plot the first value. So this is for y and this is for y dash. Okay, I draw it in black lines and the analytical solution I use the blue round circles. Okay, and this is for y dash. I extract the second row and this is an analytical solution again plotted in blue circles. Okay, I'll clear this off. Let me run this. Of two solutions like this. So you can see how closely things are matching. So this black curve and the blue curve, that is the analytical solution and whatever I got using BVP solver. For this is for y, it is closely matching. You can see how it is exactly overlapping. And this is for y dash. Is this clear how to solve this BVP problems? If you're like, if there are slight tweaks also, you should be able to code that. Since there are nobody's asking any doubts, I'll move on to the next question. Okay, this is solving using finite difference. So I'll give you a few minutes and then we'll discuss the answer.
Ma'am, you are not audible.